So first of all, thanks for the invitation to come here. It seems that there's a lot of related work going on here, so we are excited to be here and chat with you. So the work that I'm going to talk about here is work that I started about a year ago when I started working on my postdoc with Garth. And the basic motivation behind this work is actually almost trivial, and I think I'm preaching to the choir here. System reliability is really important. And system reliability is really important for several reasons. First of all, failures can be very expensive. Even a short time of downtime can be expensive for businesses. Also, system flakiness is a major source of user frustration. So there's this really nice study that has been done in Great Britain among college kids, and what the study says is 25% of college kids in the survey have seen peers kicking their computer, and 2% claim that they have hit the person next to them in their frustration at some point. So system reliability is important, and it's a major problem in today's systems. The bad news is that a lot of people expect this problem to become more serious in the future. And the reason is that the current trend in building systems, and you at Google know this pretty well, I think, is to scale out instead of scaling up. So systems have many more components. And many more components means there are many more components that can fail potentially. So if you take one example, this data that we got from Los Alamos National Labs from one of their high-performance computing clusters. This is a cluster that has around 1,000 nodes, standard commodity hardware, 4-way SMPs, and they observe about 100 node outages per month. So this is the scale they currently have. They are working right now to get up to petascale. That means 1,000 times more components. And the question is, with petascale computing, does this mean instead of 100 outages per month, will we have 100,000 outages per month that we need to deal with? So system reliability is a big problem, and a lot of people fear it's going to get worse. So what makes it so difficult to make systems reliable? So first of all, if you want to make systems more reliable, you have to understand what makes them unreliable. So what do failures look like? What's the most common root cause of failures? What are statistical properties like the time between failures? And unfortunately, failures are not very well understood. And we're not the only ones complaining about this. There are quite a few researchers that have said in the past, a lot of work in the area of system reliability is based on anecdotes or simplistic assumptions. So why is this? It's not that researchers are just oblivious to this problem or ignorant. It's just that there's hardly any data publicly available that you can use. So vendors or companies have data, but it is sensitive data, and they usually don't share it. So researchers are stuck with anecdotes and simplistic assumptions. And that's exactly what motivates our work. So our research agenda that we started working on last year is basically trying to collect data from a lot of sites and making it publicly available to create a public failure data repository. Then the long-term goals are to analyze this data, to learn more about what do failures in the real world really look like. And then how can we exploit this data? So are there any statistical properties, for example, in the data that we can exploit to make systems more reliable or to manage systems in a better way for higher availability? And I will talk briefly about all the three topics. I'll focus on the second topic, but I still want to give you a brief overview over the first and last topic as well. So starting with the public failure data repository that we want to build. So what we've been doing in the last year is basically talking to a lot of sites and trying to convince them to give us failure data. And we have been successful with doing this at 3 different sites. And we have data that spans 26 large production systems at those 3 sites. And some of this data is actually, at this point, already publicly available. In the long run, we would really like to see this hosted by Usenix. Usenix has agreed to collaborate with us on that. Have this hosted at one neutral place where you can put all this data so that it's accessible for everybody. So giving you a brief overview of what data it is that we have. So the first data set that was made available to us is really a cool data set. It comes from Los Alamos National Labs. And the reason that it's really cool is that, first of all, it spans 9 years of data. It covers a lot of systems. It covers 22 high-performance computing clusters with several thousand nodes in total. And it contains a record for any node outage that they had during those 9 years on any of those systems, including root cause information. So that's the first data set that we got, and we're really excited about that. We also got data from 2 other sites now. We got data from the Pittsburgh Supercomputing Center on one of their high-performance computing clusters, and from one internet service provider who wants to remain anonymous. And the data that we got from these two other sites actually are mostly hardware replacement logs and disk drive replacement logs. So we have been working with those data sets over the last couple of months. And what I really want to do in the remainder of this talk is give you a brief overview of what we found in our analysis of this data. And as I said, there are different types of data sets. And I will break down the analysis accordingly. So I start by looking at what do cluster node outages look like. And that's the Los Alamos data that spans all their cluster systems over the last 9 years. And then I look at specifically storage and hardware failures, because data from the other two sites contains this type of information. And in the end, I look a little bit at statistical properties. And it turns out that many of the statistical properties are very similar no matter whether you look at cluster node outages or hardware data. And that's why I'll do it in one topic together. OK, so let's start with the Los Alamos data on cluster node outages. So let me give you a brief overview of what those systems look like so that it actually makes any sense of what the data means. So Los Alamos has basically two types of clusters. These are all large clusters, and they're either made of standard commodity components, 2 or 4-way SMPs, or they're made of pretty large individual nodes, NUMA nodes. So the interesting part, and the reason I'm telling you this is, the majority of the systems falls into this category. So large clusters made of commodity hardware. So although their usage of those systems, high-performance computing applications, might be not so representative of many other systems, the hardware is actually pretty standard hardware that you see in many other contexts. So what's the data that we got for those systems? So as I said already, this data covers 9 years on 22 of such large clusters. It contains records for all node outages during this time, and that's a total of 23,000 records. So when we started to analyze this data, one of the questions we had was just, what do failure rates look like? If you're the administrator of one of those large systems, how many failures do you have to deal with? Is it like 1 failure per week, 1 failure per day, a couple per month? So what this graph shows you here is basically the average failures per year for each of the cluster systems. So each of these bars corresponds to one cluster. And the color coding refers to what type of hardware was used in each cluster. So we cannot release any vendor-specific information. In fact, we don't even know vendor-specific information. But we know that all the blue systems use the same hardware. The same hardware comes from the same vendor and the same CPU memory models. So the blue systems, for example, have MD3 4-way SMPs that were introduced in 2001, put into production in 2001. As you can see, they are quite different systems. There are also, for example, green systems that are made of NUMA nodes, and they're much older. They're put into use in 1996. So there's a large variety of different systems. And if you look at the failure rates per year for all the systems, what you notice is that there's a very big variability, right? There are some systems that have a couple of failures per year. There's some, like this one, that have almost 3 failures every single day, node outages every day. Now, what's interesting is that even within one type of system, within only the blue systems, there's a big variability. And that, yes?
Are the clusters all the same size?
Exactly. So the reason is that those clusters do have very different sizes. So this cluster has more than 4,000 processors. This has only 128 processors. And this happens to be the smallest cluster of the blue clusters. And this happens to be the biggest cluster. So to make more sense of this, what you really want to do is normalize by the number of processors, by the size. And if we do this, we get this graph. What you see now is that, first of all, the failure rates are much more similar across the systems, even though they have different sizes. But if you normalize, it seems basically that the failure rates grow somewhat linearly with the system size, because if you normalize, the rates are pretty similar. What is also quite interesting, I think, is if you look at different types of systems, even across different systems, the failure rates are very similar, not only within one type of system. I mean, even the red and the blue and the green systems have relatively similar failure rate if you normalize by the size of the system. So this data was all on how do failure rates vary across the different types of systems. Another question is, if you look at all the nodes in one single cluster, how do failure rates vary across the nodes in a cluster? And we assume that all the nodes have exactly identical hardware, because that's what's the case for those systems. And And if you look in the literature that does research with these type of systems and runs simulations, the common assumption is that all nodes are equally likely to fail. These are identical nodes, so they're all equally likely to fail. So we took the data for one of those systems. We checked it for all of them, but I'm showing you data for one of those systems. And this is the number of failures for each of the nodes in this particular cluster. And we did some statistical analysis, and we find, not surprising, that there are clearly some outliers here. You can see this without doing any statistical analysis. There are clearly some outliers, like nodes 21 to 24 have much higher failure rates than the other ones. And the question is, why is this the case? They are really identical nodes in terms of their hardware. So we went back to the Los Alamos people and talked to them, and what they told us is that those outlier nodes are used in a different way. While most of the nodes in the system are actually compute nodes, those nodes are either visualization nodes used for visualization applications or front-end nodes. So what this seems to indicate is that the failure rate does not depend only on what hardware you're using. It depends on what workload you're running on the nodes. So what is also interesting, was there a question?
I'm just confused by the y-axis. If you were failing about once every 3 years, how can you have 300 failures for a given node?
So this is the number of failures during the entire lifetime.
Of that machine?
Yes, of that machine. And that happened to be this really old system that was introduced into 96, and that's still being used today. So you have to normalize this by 9 years. So what is interesting is that even if you remove those clearly outlier nodes, if you look at only the compute nodes, there's still a skew in the distribution. So it seems nodes are not equally likely to fail. And for the compute nodes only, we don't have a good hypothesis at this point why this is, why some nodes just statistically seem much more likely to fail. So those graphs were all dealing with failure rates and how do failure rates vary across different parameters. This data also included information on the repair times. So how long does it take for the different types of systems to fix a problem? So this is exactly the same graph for those 22 systems showing the median repair times in minutes. So again, what you see is there's a lot of variability, right? There's some systems that have repair times of 10 minutes. There are some systems that have median repair times of more than 300 minutes. The trend that's different here now is that within one type of system, the median repair times seem to be very similar. But if you look at the rates across systems, if you compare, for example, the red and the blue system, those are both systems of roughly the similar age, similar hardware. They are 2- and 4-way SMPs, respectively. Still, the repair times, the median repair times, are quite different. And the question is, why is this the case? So one, yes?
Is your definition of failure binary, or do you distinguish between types of failures? Do you have on what type of failure?
So the definition of failure for this part of the talk is node outage. So something went wrong in node that caused the node to go down, and somebody had to come in and fix it. It would not take into account any flakiness that didn't cause the node to go down, anything where the application top basically continued running and the failure that could be masked would not be recorded here. Mm-hmm.
Does repair involve, what kind of repair does it involve? Does it mean rebooting the system, or does it mean replacing the faulty hardware?
Anything. It means anything. It means anything. And that's why I'm giving median repair times, not mean repair times. There's a very big variability because some problems are fixed by reboots and other problems are fixed by hardware replacement that might take some days.
Okay.
Yeah, so one thing what we were wondering is why, for example, between the blue and the red systems, why is there such a big discrepancy in terms of the repair times, since these seem to be relatively similar systems? And one hypothesis that the Los Alamos people told us is that simply priority. So it turns out that those red systems are used to run applications related to the nuclear weapons program at Los Alamos. So it seems that they just put higher priority on fixing those problems fast. So one really obvious question is, if there's a failure, what was the root cause? So what went wrong? Why did this node go down? The nice thing about this data is that it actually does have root cause information. So for every node outage, the root cause is specified in one of 6 categories. It's hardware, software, network, environment, human, and unknown. And if you look at the relative frequency of those, what you find is this graph here. So this is broken down by type of system, hardware type of system. And the first overall trend that you see is that in each of those bars, the green fraction is pretty big. Green is hardware and makes up about 50% for all of those systems. So 50% of all failures that they deal with in those environments are due to hardware. Another pretty big component with around 20% relatively consistently is software. That's the yellow bar. Unfortunately, there's also a relatively big fraction of blue area. And blue are cases where the root cause is unknown. And what this means is we cannot really conclude that network problems, environmental problems, human error are negligible because they might be in this blue area. What we can conclude is that hardware seems to be a really significant factor, and software definitely too. And if you look at their contribution to the repair times instead of just the frequency, the relative frequency, you see the same trend even stronger, even more green.
So this includes, the notion of failure includes reboots, right?
Yes.
Seems very surprising that hardware is such a large component that reboots are included.
Actually, there are quite a few hardware problems. Maybe I should clarify what hardware problem includes. There are actually also a lot of hardware problems that can be fixed with reboots. Because it turns out so there's actually more detailed information. There are not only these 6 high-level categories, there's more detailed information. So if it was a hardware problem, what was the hardware problem? What is CPU, memory, disk, what was it? And it turns out that a lot of the problems there are due to memory, but it's not a memory DIMM being fried and having to be replaced. It's very often parity problems. So the ECC couldn't correct the number of errors that has occurred, so you just reboot, and those problems do go away. So actually, even within the hardware category, there are quite a few problems that can be fixed by reboot.
Do you have data on how the unknown problems were fixed?
So in general, we don't have any information on how any problems were fixed. So what I just said, for example, that memory problems often are fixed by reboots and they are parity related. That is information that are obtained by talking to those people. So the data includes information on repair times, which allows you maybe to conclude some things, like if the repair was 3 minutes, most likely it was a reboot and not a hardware replacement.
So then the graph here you have there is a distribution of hardware, software. That's not something we can quite rely on because unknown factor is like 20%. You have systematic error of 20% you can account for anyway.
That is true. So we cannot say anything about human environment and network problems because they could be in there. What we can say is that for most systems, at least 50% of problems are due to hardware, and at least 20% are due to software.
Question. So what are the sort of, I don't know if this information is available, what kind of things would be contributing to software failures at the node outage level?
So for their applications, so they do give, for a lot of cases, they do give extra information on software failure and what it was. And it seems to be the case that operating system software problems or scheduler software problems or file system problems seem to be the major contributors. But there are also a lot of entries that just say software general, where it's unspecified what software. So I cannot put percentages on that exactly.
So across all clusters or just Los Alamos?
This is all clusters at Los Alamos. So this is 22 clusters at Los Alamos.
So do you have like similar data for the internet service center that you?
No, unfortunately not. For the internet services, we have hardware replacement logs. So we see only hardware failures. And for some of the data sets, we know which type. We have more than just disk failures. We have also CPU, memory, other types of failures, but it's all hardware only.
I was going to make a suggestion that we try to limit the questions to clarification questions. There's so much interesting data here that we could make this last a couple of hours.
You won't be here for hours.
Yeah, afterwards.
I have planned a talk for being interactive, so don't worry, you won't be here forever. So this was really a very high-level overview of our analysis of the cluster node outages from the Los Alamos data. What I want to do next is look at storage failures specifically. And just to remind you, we have storage data from 3 different sites, storage failure data. Actually, most of this data includes hardware failures in general, not only storage. And this spans different types of drives, SCSI and fiber channel. We don't have SATA drives at this point, so we're very interested to hear what you have to say if you have it. The counts of drives, the number of drives that is included, usually is on the order of a few thousand for most of these data sets. And usually the duration of the data sets is on the order of a few years. So for us, that's relatively large data sets. I know that for a lot of vendors or people that run really large systems, this is maybe not so large, but for us, this was still very interesting. So starting by a very general question. So if you look at disk failures, how frequent are they compared to other hardware failures? So the data sets that we have are hardware replacement logs. So what we can look at is which components are most frequently replaced among all the different hardware components. So what these three tables show you is for 3 different systems that we have this information for, the top 10 most frequently replaced components. And to make it easier for you, this is where the hard drives are. So for all those 3 systems, hard drives are among the top 3 most frequently replaced components. And in some cases, they make up to 50% of all components being replaced. So this means disk failures are relatively frequent compared to the failures of other components. Another question is, what is their actual failure rate? So if you have a certain population of disk drives, say 1,000 drives, what percentage do you expect to fail every single year? So one way to estimate this would be all drives come with data sheets. And those data sheets include a number that is mean time to failure. And for modern drives, that tends to be around 1 million hours. So a mean time to failure of 1 million hours would roughly correspond to an annual failure rate of 0.7% to 0.9%. Okay? Now what we did is we looked at the data and we looked at the annual replacement rates. So how many drives were really replaced in the field? For a given population every year, what percentage was replaced? So this is the different data sets and the ARR in percents. So what the solid and the dashed line here tell you is the expected annual failure rate that we computed from the data sheet. The bars show you the annual replacement rate. And what you can see is that for all data sets, basically, the replacement rates are much higher than the failure rates that you might expect based on the datasheet MTDF. Typical values seem to be around 3%. We're currently trying to get data from other sites to confirm this, and it seems that the 3 to 6% range is very common. We have some data sets where where replacement rates are even higher, on the order of 6 to up to 12%. We're currently still trying to verify why this might be. We're trying to verify, for example, we know for all these sites the drives were less than 5 years old, up to 5 years old. And we're not sure at this point whether these data might contain data for drives that are older than 5 years. So what this says is the field replacement process really is quite a different process from what you might expect based on datasheet mean time to failure. Mm-hmm.
I suppose that the disks are not replaced when there is no failure.
That is a very good question, because it depends on your definition of failure, right? So we know from all these sites that they replace disks only when to them the drive seems failed. But how do you decide whether the drive is failed? So what you typically do is you perform some type of test, and you decide if based on this test the drive seems to have problems, you discard it. So what a lot of disk manufacturers tell us is that the rates that they see are lower. And this could be, for example, because sites are pretty aggressive when replacing drives, because they err on the positive side, while manufacturers maybe make different assumptions than the sites do. So basically what this says is this is the percentage of cases where people running those systems decided this drive to us looks like it's failed. Mm-hmm.
I'm wondering if the disk drive manufacturers have actually told you that you can expect a lower annual failure rate than you're seeing. It's not obvious to me that the MTBF and the annual failure rate are actually inconsistent.
There are different things, right? So first of all, the MTDF predictions are made under certain assumptions. So the drive manufacturer assumes that, for example, operating conditions are at a certain level. For example, temperature stays within certain thresholds, certain handling procedures are followed, and the discrepancy might just be because, for example, sites using the drives abuse them in a different way than manufacturers were expecting it.
I was actually wondering something even more basic than that. Just as a matter of statistics, is there a discrepancy?
Oh, there is, yes. I mean, we did statistical tests. If you make the assumption that this data that we got for like any of these data sets, you make the statistical assumption that this data does come from a distribution that had a mean time to failure of 1 million hours, you can reject this hypothesis with very, very strong significance levels. I'm really 99.999 something significance levels. Because, I mean, some of these data sets contain like 40,000 drives. It's just highly unlikely that over a sample size of 40,000, you see a mean that's so far off the real distribution's mean. So one thing that people often complain about when it comes to this MTTF value that's specified in the data sheet is that what the MTTF value does not capture is that the failure rates might vary as a function of the age of a drive, for example. So it's commonly assumed that failures for hardware components follow this bathtub model where you have some time of infant mortality, then you have a stable life for a while, and in the end you have wear out. And for disks, it's often assumed that you have infant mortality during the first year, then you have 4 years with relatively low stable failure rates, and in the end you see wear out. So if you look at the nominal lifetime of drives, which is 5 years, you expect to see something like this. So one of our data sets, and that's the data from the Pittsburgh Supercomputing Center, actually does span exactly 5 years. And it's a homogeneous population of exactly the same type of drive that is measured over 5 years. So we said, great, so we can compare what the real replacement rates look like compared to what you would expect in terms of failure rates. And this is what we get. So what these two bar graphs show you is the number of replacements per year for the drives in the compute nodes and the drives in the file system nodes. And if you compare this to the theoretical model, it obviously looks very differently. What looks different is, first of all, there's hardly any infant mortality in the real data. We don't see any signs of infant mortality. And it seems that the wear out starts much earlier than you would expect. It seems that the replacement rates clearly are steadily increasing over time. And it's pretty large factors of increasement, even going from the first to the second year, or going from the second to the third year, you almost double your replacement rates.
Question. You didn't specify if the drives were brand new when they started in production. Is that the case?
Say that again?
The drives were brand new when they started?
Yes. So the drives were in 2001 all brand new drives of the same model that were put into the system, and they have been there for the last 5 years, unless they were replaced because the PSC decided they are broken. And you can look at this at a different granularity also. This is the same graph showing data by month of operation. And then you see maybe a little bit of infant mortality for this data set, but really not much. So it seems that the important factors are really early wear out and not so much infant mortality if you want to model failures as a function of age. Okay, getting to some statistical properties. So why, most people think statistics are pretty boring, so why do we care about statistical properties? In most work, whenever you want to evaluate the reliability of some system design, you have to make some assumptions on what, for example, the time between failures looks like. And the common assumption is that, first of all, the time between failures is exponentially distributed. And the second assumption is that failures are independent. So we decided we'll take a look at the real data and see how realistic those assumptions really are. So starting with the first assumption, the time between failures follows an exponential distribution. So what we find for both the cluster node outages and the disk drive failures, the data differs significantly from an exponential. And we did statistical testing, we did distribution fitting, but really what we find as the two key properties that make it different is, first of all, the real data has a much higher variability. So there's variability with squared coefficient of variation of up to 12. An exponential has a squared coefficient of 1 in comparison. And we find decreasing hazard rates. So what does that mean? Just as a reminder, basically hazard rates tell you the probability of a failure as a function of the time since you have seen the last failure. So if you look at the expected remaining time until the next failure on the y-axis, and on the x-axis you have the time since the last failure. If you're at time 0, that is, you just have had a failure, what would you expect? You would expect that the expected time until the next failure is just the average of the distribution. So for this particular distribution, this is 1,000 minutes. So how does this change if you have lived for, say, 6,000 minutes without any failures? How much longer do you expect to go from these 6,000 minutes? So for an exponential distribution, this would still be 1,000 minutes, 1,000 extra minutes. That's a basic property of the exponential distribution. So how does the same graph look like if you look at the real data? And this is the data for the cluster node outages. So what you can see is that the graph looks very different from an exponential. And what happens is that the longer you have been living without any failures, the longer you expect to live. So if you have been living for 6,000 minutes without any problems, you expect to live an extra 4,000 minutes. So this is one of the key properties that makes the data very different from an exponential distribution. And the same holds for disk replacement data, if you look at the time between replacements. So the second assumption is that failures are independent. And we did different tests for correlations. We find all kinds of correlations. It's maybe not surprising that failures are not really independent in the real world. We find autocorrelation. We find long-range dependence. That's one example. This shows you the autocorrelation graph for independence, where autocorrelation would always be 0. For the real data, you have much stronger levels of correlation, up to a correlation factor of 0.7. Maybe a different way to show the same data is, so what does autocorrelation mean? Autocorrelation really tells you what's the correlation of the number of failures in this time period as a function of how many failures did I see in the previous time period. So if you look at the number of failures on the weekly level, for example, if I have seen in the previous week a small, medium, or large number of failures, how many failures do I expect in this week as a function of that? Obviously, if the data is independent, you would always expect the same number of failures. For the real data, and this is the disk replacement data, the number of failures that you expect in a given week is very different depending on the number of failures you've seen in the previous week. So if there was a small number of failures in the previous week, you expect 0.1 failures in the next week, compared to more than 4 failures in this week if the previous week has a lot of failures. This is basically another way to look at autocorrelation. So there are strong levels of correlations, basically, what we find. So the interesting question is, what is all this good for? So we have this data, we've analyzed it. We have found that maybe common assumptions are not necessarily realistic. The real data is not exponentially distributed. There are correlations. Can we exploit this in any way? And this is something that we've just started to work on, so it's very much work in progress. And I'll just show you 2 ideas that we have looked at where we think this data makes a difference, or knowing that the real data looks different from what people commonly assume. So the first example that I want to give you is high-performance computing systems, and the impact of the fact that the time between failures is not exponential. So first of all, if you talk about high-performance computing systems, how do they implement fault tolerance? So what they do is they have these large-scale applications that run on a large number of processors, and these applications use periodic checkpointing. So every fixed X minutes, they write back a checkpoint. If only one node that this application is using fails, the entire application has to roll back across all processors to the most recent checkpoint. So the performance of this whole thing depends critically on how you choose this fixed checkpoint interval. If you checkpoint very frequently, you have a lot of overhead because you spend a lot of time writing back those checkpoints. On the other hand, if you have really long checkpoint intervals and you checkpoint very rarely, this means that in the case you do have a failure, you lose a lot of work. You have to roll back very far back in the past. And people have some methods for how to deciding, depending on what the expected time to failures, how they choose this fixed interval. So what we were thinking is it really the right thing to choose a fixed checkpoint interval? So why do people have this fixed interval? They basically have this fixed interval because they assume at any time the probability of the failure is the same. So we have a constant failure probability, so we use always the same checkpoint interval. What we have found in our work is that, so for example, depending on how long it has been since the last failure, the expected time until the next failure is very different. So maybe we should use this information. And we tried exactly this. So we tried to update the checkpoint interval based on the time since the most recent failure. So if it has been very long since the most recent failure, we make the checkpoint intervals bigger. And we've tried this, and we get only moderate savings in the checkpoint overheads. It's around 7%. One of the reasons I think for why these savings are so moderate is that you really gain when you're in this end here, when you haven't seen a failure for a really long time, and these are relatively rare data points. So we didn't gain too much there, somewhat. Another way of doing this would be, instead of just looking at the most recent failure and updating checkpoint intervals based on that, what if we take the whole last week into account? I look at the whole last week and I see how many failures have I seen there, and I base my checkpoint interval on that. And we actually find that you can have big savings if you do that. You can save 60% in your checkpoint overheads. So going back to the disk replacement data and what might be the impact on how we deal with disk failures. So one common way to protect yourself from data loss is use a RAID configuration. And when you put together a certain RAID configuration, you want to know what is the expected time until I lose any data in this particular configuration. So basically what this depends on is the probability that if you have lost one disk, that while you're reconstructing the data from the other disk in the RAID, that a second disk fails. Because if you have single parity, as soon as you lose two disks out of a RAID, you lose data, actually. You cannot reconstruct anymore. So the question is, if you estimate this probability, the probability that you lose a second disk while you're recovering from another disk failure, how does this probability depend on what assumptions you make? Whether you use the exponential assumption or whether you use real data, and whether you take dependence into account or you do not. So starting with a simple way. So a simple way of estimating this probability is taking the data sheet, mean time to failure, making the standard assumptions that failures are exponential and independent, and we computed based on these assumptions the probability that within the first hour of reconstruction you have a second disk failing. And that's this tiny little purple bar here. So the probability is 0.1 times 10 to the minus 3. So we also looked at the real data, and we did the same estimation based on the real data. And that's when you get this long green bar, which is actually 2 orders of magnitude higher than the purple bar. So this simple estimation wasn't working very well. And you could argue it's because we have seen already that the datasheet MPTFs are not very representative of replacements. So I should maybe take the real data and take the mean time to failure based from the data. So we did that. So we took the mean from the real data. We still assume exponential time between failures and independent failures. And if we do that, we get the blue bar. So we're getting closer to the data, but it's still pretty far away. Is there a question? Okay. So finally what we did is we matched different distribution to the real data, and we found that the Weibull distribution is one good fit. So we did the same calculation with the Weibull distribution. We take a Weibull distribution matched to data and estimate the probabilities based on the Weibull distribution, and that's the orange bar that you see. So you're clearly doing much better if you make those more realistic assumptions. And that is the case not only if you look at 1 hour reconstructions, it's also the case if you look at the first 3 hours of reconstructions or the first 6 hours of reconstruction. So there's this consistent trend that if you want to have realistic estimates of losing any data in a RAID configuration, it is really important that you take the realistic properties of failures into account and you don't make simplistic assumptions. So to conclude, basically, in our initial analysis of the data that we've been collecting in the past year, what we see is that, first of all, a lot of common assumptions are maybe not realistic based on this data. The questions here are, so obviously this gives you motivation for future work, but what should the future work be? So first of all, how do we build more realistic models? If those assumptions that we're currently using are not realistic, what should realistic models look like? So obviously you could build really complex statistical models that capture every single detail, but then you lose all the intuition about your model. So what's the right model that captures enough of the real world, but is still such that you can deal with it and you can work with it? The long-term goals that we're interested in is really, how can we use this data? So how can we exploit the data to build systems in a different way? And some of the things that come to mind are, so can we exploit some statistical properties, like we're looking into checkpointing, the 2 slides that I just showed you. Can we do better checkpointing if we take statistical properties into account? In the long run, can we automate things and do system management more proactively. So if you have a lot of data, can you look at the data and can you predict that a failure is coming up? And that's something that, for example, Edward, that you guys in some way have looked at by looking at smart data and disks, and that could be done at very different levels in the system. But that's something that we're just starting to work on. And that basically concludes my talk.
Questions?
With the autocorrelation?
Yes.
So some systems, when you have more failures in the past, you're more likely to get failures
Right.
in the future.
Right.
But and you have another correlation of the some systems are more likely to fail, some
Yes.
systems are more likely to fail.
Yes.
So do you have the two correlations put together? Is it the identity of the failing nodes that I have 100 nodes that failed this week, and next week I expect to see more nodes that fail, and how many of these 100 nodes fail this week will carry over to the next week's failure?
So what I have done is I looked at the autocorrelation at two different ways. So I looked at it taking the entire system, like this entire cluster, and I looked at the times that I see any failure in this cluster, and that shows autocorrelation. I also looked at only individual nodes. So if you take, for example, one of those front-end nodes, which has a higher failure frequency, and you look at the autocorrelation only within this data stream, only focusing on one of those nodes, and you still see autocorrelation. And in general, also the statistical properties are relatively similar. If you look only at an individual node, the average failure rate is higher, for example, for the front-end node. But a lot of the basic statistical properties, like the decreasing hazard rates, the high variability, autocorrelation, they seem to remain the same.
So you showed that the use of the node had a tremendous influence on failure rate. Now, were those really homogeneous hardware? Were those
Yes, they were.
So it was strictly a function of the software that was running on it?
Yes. Maybe, front nodes maybe use more complex software, additional software. Maybe they're used differently. They have many short requests, many users logging in for a short time, doing something, and then going away rather than running this long-running one big application. But we don't.
Crashing disk heads or something like that.
Yes, and we don't know that. So we're trying to get more information on what exactly the workload looks like. And what they provided us with so far is job logs. And they do contain information on, for example, the CPU utilization and who the job came from, which user the job came from, how many nodes it was using, things like that. But we haven't really had a chance to look at that and trying to correlate which factors of usage do affect the failure rate.
I had two questions. One was, did you notice any mass scale sort of deaths, both temporally and spatially? Because most of these analyses sort of are looking at it and assuming individual node failures.
Yes, we do see that. So I looked at, when it comes to the node outages in the HPC clusters, I looked at correlations between nodes. And I mean, obviously, for example, network failures, you have a really high correlation because network failures do tend to take out a couple of nodes. There is quite some correlation for software failures as well, and I don't have a good explanation for that. And it tends to happen in 28-day periods. So it might be something that these are the periods in which they upgrade the software, but I don't know that. For disk drives, you definitely see many more cases where disks fail almost instantaneously than you would expect if they just statistically randomly fail. And I don't have enough data at this point to say why some of the disks fail almost at the same time. So we have gotten, for example, temperature data from the PSC, and we have gotten data on when they had power outages, because they think that the power spikes that come with power outages might cause some of this behavior.
The other question is related to the workload. One of the slides you had early on said the workload made a dramatic difference, and I can very easily believe that. If you're looking at the usage of a cluster over a 5-year time period, you expect the workload to dramatically change in that time period.
Right.
The issue of how frequently things fail, sort of no longer is sort of a harder phenomenon, but actually how these things actually
Yes, yes. So we have different indications of how usage might affect things. One is looking at front-end nodes versus compute nodes, and they have a very different behavior. But it's true that over time, usage behavior changes. And we actually do also see, although didn't show this in the graphs, that the number of node outages in a cluster does change quite dramatically over time. And it's not in the intuitive way necessarily where you expect infinite mortality, then it goes down. No, for some of those classes, actually, it starts low, then it goes up. And one of the hypotheses is that this is because of usage, that as the system gets used more, also the failure rates go up.
On the 5 years of data on Los Alamos, did they learn anything specific about a root cause and then fix, and did that cause the failures to go down?
So I don't know any specific anecdotes. I know for sure that they learn more about root cause analysis as time goes on. If you look at the breakdown of root causes as a function of the age of the system, in the beginning, in the first couple of months, almost all the root causes have an unknown mark there. They couldn't attribute it to one particular root cause. And as time goes on, they are much better able to say what was the root cause.
Yeah, but in the case of on the table that you provided, it was like one big bucket for hardware.
Mm-hmm.
What I'm asking is there any granularity there as to CPU, memory, hard drive, power supply, motherboard, for instance?
So you're asking whether this breakdown, the more detailed breakdown, changes over time because they've made changes to the system to fix things? And I think for most of the hardware problems, it's very hard to do anything about it. So, for example, Los Alamos is at a relatively high elevation, so they have more cosmic rays, and they have maybe more bit flips than others. And that's what causes, for example, more memory and CPU problems due to this issue. But there's not much that they can do about it other than deciding that maybe next time they use a different hardware because they had, for example, one CPU model that happened to be very susceptible to this kind of problems because it wasn't protected very well. And for the next system, they use a different type of CPU, but it's hard for them to fix anything when it comes to those problems.
Were there any periodic or preemptive upgrades and maintenance repairs to the system?
There were, like the Los Alamos data does contain information on maintenance work, and we didn't count outages due to maintenance as outages, so I didn't include any of the maintenance work here. It would be interesting, though, to maybe correlate how the points in time when they did maintenance, how they correlate to the node outages that they observe, and I haven't done that analysis yet.
Or is there any set of systems that were maintained and upgraded versus others that weren't stay there for the whole lifetime?
I haven't specifically looked for that, but I wouldn't think so. So I think that those systems are managed in a pretty consistent way. So it's basically the same policies that are used for all these systems. So I think that the systems would see the same maintenance policies, for example. But I cannot say that for sure.
Do you know whether their diagnosis tools for detecting errors and tests changed over time or changed very much over time?
So my impression is that a lot of the diagnosis tools that they use are tools that they build themselves. I mean, obviously, all these systems come with tools that the vendor provides, and these will change because they use different vendors, and if they have a new system, those tools are different. But we just got some error logs, for example, out of them that were collected by some of those vendor-delivered tools. And it turns out that they don't use this data, for example, at all. They seem to really rely mostly on the software that they build themselves to monitor systems. And I don't know whether they've changed anything in their policies or what they monitor and how they make decisions over time. But I could find it out when I talk to them.
That could obviously affect sort of what they consider as a bad hard drive, for example.
That is true. So when it comes to those high-level policies, like how do you attribute a certain outage to one of those categories, they have used consistent ways of doing this throughout the years. And it's actually consistent policies also across all the cluster systems. So they have weekly meetings where the operating staff and the administrators meet, and they decide these are the categories, and this is our procedure for deciding which category a given node outage falls in.
Is there a relation between the seek patterns and the disk failure?
I would like to know the answer too. I don't know because in this data we don't have information on the usage of drives.
And likewise, correlation with the power supplies? Does it relate?
So correlation with power supplies might be there. So we know that anecdotally power outages have a correlation with failures. I haven't verified this, but I have the dates of power outages, so I can do this now. I just have to find the time to do it. Any more questions?
Thank you.
Okay, thanks.